This is Thermodynamics. The date is the 21st of February, and we are beginning our discussion of Chapter 4. This is going to be a very short lecture, probably about 15 minutes. The time right now is 11:18 a.m., and I'll have to end no later than 11:40 a.m. So we're just going to have a brief introduction to Chapter 4. Chapter 4 pulls together some of the ideas that we have covered so far in our previous chapters, and basically we're going to talk a little bit about work, and we're going to talk about changes, internal energy, and enthalpy. But the title of Chapter 4 is Energy Analysis of Closed Systems. And this is the beginning of our discussion of the second law of thermodynamics. And the basic framework for this chapter is energy can neither be created nor destroyed. So if we take the energy in a system, if it's closed, that means that only work and heat are forms of it, the only forms of energy that cross the boundary. If we have an open system, in other words, if we have mass moving through the system, energy can come and go with the mass. However, work and heat are the only two ways that energy can enter or leave a system if we don't have mass crossing the boundary, and that is the definition of a closed system. So for a closed system, if we take the energy at time 1, and we add to that the heat that goes into the system, and we subtract from that the work that the system does, that will be equal to the energy at time 2. Now we've discussed the forms of mechanical energy, which are potential energy, kinetic energy, and for the most part, internal energy. So we can say Q in minus work done by equals PE2 plus KE2 plus U2. All right? So this is always the framework that we're looking at. Now let's go back and look at this problem. This is one that we just worked. We have an energy state here. This would be E1. There's no potential or kinetic energy, so this is just basically the internal energy of the system. We have energy at state 2, which once again, there's no particular changes in potential or kinetic energy, so this is just U2. So if this is at a different energy state than this, what happened between the two? Well, the answer is that heat either went in or went out of the system. There's no work done in this particular case. There are other cases that we've examined that have work done. For example, let me do this. If you recall from our previous discussion, heat is energy that moves by a temperature gradient, or I should just say from high temp to low temp. So remember, heat and temperature are not the same thing. Work, on the other hand, is energy that is done by a force acting through a distance, and that often in terms of thermodynamics this turns out to be a PDV term. And we discussed this a long time ago. I don't expect you to remember it, but this is basically what the integral comes up to for a lot of closed systems. So if we go back to the other problem that we worked for homework today, you can see that we have a falling piston. This has more volume than this. That means that work has been done on this system, because PDV is going to be a negative term, isn't it? In other words, P remained the same, V changed, so dV is negative, and so we have an integral of PDV that represents work done on the system or a compression. All right, so what we discuss in the beginning of Chapter 4 is a type of work that we just looked at with that system, which is called a moving boundary work. Now work always goes back to this integral. Well, it always goes back to this integral, really. But if you remember, remember force per area is equal to P. So for force is equal to P times A. So if we substitute that, we can say P times A times dV. And if you have something like a cylinder fitted with a piston that has a constant area, dV here is just going to equal that constant area times dx. If I call this dx, how much the piston rises or falls. And so in this case, the dV is equal to an ADX term, and we come out with an integral that looks like this. This should be a dx, sorry. And so this becomes this because ADX is equal to dV. So that's sort of the basis for this idea. Now the first thing about work is dependent on the path you take to get from state 2 to state 1. So in other words, you can do more or less work depending on how you get there. This type of a case that we discussed, first of all, is called an isobaric expansion or compression. Okay. So how much work is done from state 1 to state 2 isobarically? If P is constant, which is the definition of isobaric, comes outside of the integral, and we just have P times delta V, or P times V2 minus V1. Now it's important to know P delta V is work only in the case that the pressure remains constant. Okay? The other thing is that any time you can plot pressure versus volume, what's another definition of an integral? A definite integral between 2 points. If this is V2 and this is V1, what does this area represent as far as an integral? It's the integral of P dV. So in other words, work is also here. If you have a function, work is the area under the curve. You guys learned that in calculus, right?
So it's the answer to the integral.
Sorry?
So it's the answer to the
It
integral.
is. That is correct. So since it's the answer to the integral, since the area under the curve between, we're talking about definite integrals only, not indefinite, but if you have a definite integral and you have your beginning point and your end point, the area under the curve is the integral of that function. So if we have PV plotted together, the area under the curve can be work as well. This can be very effective and useful because pressure is not always constant, is it? We already know that. You can change the pressure. If you change the pressure, then what? Well, there are two other types of work, one of which we love that never actually happens on a test, but isochoric, which is also called isovolumetric. If you have a rigid container, like this, so temperature changes, pressure changes, but the size of the container doesn't change. When we look at the work from state 1 to state 2, integral of P dV, if dV is 0, what's work? If you don't change the volume, what's the value of this integral? And that means that the work from 1 to 2 is 0. So if you don't have a change in volume, you do not have any work done. It's just like with this table. If I push on it and push on it with a ton of force, but it doesn't move, I'm not doing any work. I'm exerting energy, but I'm not doing any work. The table has to move in order for there to be work done. The piston has to move in order for there to be work done. Okay, so now we know constant pressure, we know constant constant volume. If you have constant temperature, which is called isothermal, you have to have P as a function of V, because otherwise you can't do this integration without having some function of these variables. So let's just say if it's isothermal and, for example, an ideal gas. We know that P times V is equal to nRT. P is equal to nRT over V. We can substitute that expression here, and we can say it's equal to nRT over V dV. If it's isothermal, N is always constant, R is always constant. If it's isothermal, T is also constant. So you can say it's nRT times the integral of dV over V. We have to go from V2 to V1. So it's nRT times the natural logarithm of V2 over V1. Right. And the last case that we're going to examine today is the boundary work for something called a polytropic process. Polytropic just means many states. But a polytropic process that we're interested in is one where P times V is not a constant, but PV raised to some number, just the V raised to some number, is a constant. Or in other words, P1 V1 to the N is equal to P2 V2 to the N. The reason that we're interested in polytropic processes is a lot of natural combustion processes, including internal combustion in a car engine. Hydrocarbon combustion follows this pattern more or less. So that's why we find it interesting. All right, well, if P V to the N is equal to any of those things and is also equal to a constant, take our integral, work from 1 to 2, P dV, right? We can plug in, let's just use this part. This should be an N up here, sorry. We can plug in this and we can say P as a variable is equal to P1 V1 to the N over V to the N. And we can plug that in. And we can say, instead of putting in the variable P, we can say P1 V1 to the N over V to the N dV. And then we further know that P1 V1 to the N is a constant. So we can pull that outside of the integral. And then we have a dV over V to the N, which is V to the negative N, right? So when we do this integral, it becomes, if you think about this as being V to the negative N dV, this is going to become V to the minus N plus 1, or 1 minus N, over 1 minus N, evaluated at V2 and V1. And so we have that the work done in a polytropic process could be thought of as P1 V1 to the N times, if we plug in V2, V2 to the 1 minus N minus V1 to the 1 minus N over 1 minus N. All right, now if you think about it, because it's a constant, P1 V1 to the N is also equal to P2 V2 to the N. So if I take it in this form and multiply it by this, I get P2. If I multiply V2 to the N to the times 1 minus N, I get 1 plus N minus N, which is just V2. Plug it in this form, I get the same idea for the V1 side over 1 minus N. So for polytropic process, the work integral reduces to this form. All right, so what we've done today, and this is important work for your reference, we have isolated 4 forms of the integral, or we have derived or arrived at 4 forms of the integral for work. Work for a polytropic process, isobaric process looks like this. Work for an isochoric or isovolumetric process looks like this. Work for an isothermal ideal gas process looks like this. I guess we've really done 5, because if we just have a general function of P and V, or a graphical relationship between P and V, we can just find the area under that curve, and that would be our fourth way of looking at it. And then for a polytropic process, we have work is equal to P2V2 minus P1V1, all divided by 1 minus N. So we have 5 forms of work depending on the relationship between P and V. Yeah, of course. How's that? All right. So at this point, do you guys have any questions? All right, so what your homework is going to look like is just finding work for some different kinds of processes before we pull all of that together into closed system analysis. And let's do, for homework, let's do 4-5. That's a polytropic process. This one has stops. I would like one. Uh, 4.8, 4-8, which is a isobaric. 410, which is a relationship that you may have to graph. You may not have to. You may be able to plug that into the integral and come up with something just the same. And then 411, which is for isothermal. All right, and there's none for isochoric. Isochoric is always 0, so that's the good news. All right, so there's your homework, and we'll see you guys Thursday.